Okay, so good evening, good afternoon, good morning. So, okay, I'm Tetsu Tanaka of Tokyo University, Japan. So I'm chairing this session, the session number 5. Okay, so we have in this session we have one keynote and 2 regular papers. Okay, so and then one more. One more things. So if you have any question, please use chat or please use the please say that directly. Okay. Okay, so let's start the session 5. So that's the first. We have a keynote. So the keynote, the title is the keynote is Advanced Packaging Enablement for Compute. So they're presented by the Dr. Patti. So Bob is the president of NHanced Semiconductors. He has spearheaded the development and the delivery of cutting-edge 3D and 2.5D intelligent technology for high-energy physics, medicine, automotive, military, high-performance computing, and other fields. He has managed hardware engineering teams in several organizations, including successful startups. Bob received 2009 Semi Award for North America for his pioneering work in 3D IC integration and the 2015 3D Insights Individual Achievement Award. Okay, Bob, are you ready?
Yes.
Okay, please, go ahead.
Okay. I think you need to enable my screen sharing.
Okay.
There we go.
You should be able to share the screen.
Yep.
Okay, I can see. Okay.
Okay, very good. So what I'm going to go through today is a look at advanced packaging for specifically use in computing devices. I thought that would dovetail nicely with the next 2 talks. And I'll start with a brief history of advanced packaging and the adoption. If we look at it historically, I'm going to get rid of some other stuff on my screen here. Hopefully you guys don't see all the things that are left. Really, the first adoption was in the area of imagers. Sony is well known as being a company that licensed the Ziptronics technology for the hybrid bonding, early on the covalent oxide bonding. And from there, almost at the same time, GPUs, NVIDIA and AMD started looking at using the hybrid memory cube. AMD pioneered a lot of that. The industry took about $1 billion gamble to develop 3D around GPUs and the hybrid memory cube. Silicon interposers, those were all new technology 10 years ago. From there, what we're currently seeing is the industry is moving to adoption in the area of microdisplays. There's a number of customers that are interested in that. I've kind of glossed over the fact that certainly things like the hybrid memory cube and the stacked memory that Micron developed, which I actually have a picture of to the right, those have been going on also for about 10 years. Today, at least NHanced, what we're starting to see is a lot of people interested in doing compute devices. It is mostly being done in the IDM areas, and people have verticals such as Intel and AMD. Xilinx certainly was an early adopter and well known in their FPGAs. I kind of put them in the category of compute devices. A lot of the large devices were geared towards those type operations. That is being driven by memory bandwidth and reduction of latency. A lot of it is targeting heterogeneous compute, and it's a good fit. Incorporates the adoption of chiplets AMD has a number of different devices in this area. And we're seeing more and more of it being used because of photonics being added on to the compute platforms. And this is not only for I/O, which is a pretty obvious solution, but we're seeing a lot of photonic compute starting to be developed. And it's because of recent work for AI that incorporates photonics, because you can basically do a vector multiply in photonics, and it's, you know, orders of magnitude less power than doing it in any digital format. So it's driven by the much lower power per bit op that you can get out of it. And of course, the other aspect of it, and the Xilinx FPGA is an obvious example, and AMD has spoken to this. You can effectively get very large die at a much better yield cost point with advanced packaging. So what is advanced packaging? My definition is it's the use of semiconductor manufacturing processes and techniques to perform multi-semiconductor electrical or mechanical device aggregation and interconnect to the next assembly level. This is how I differentiate it from other forms of packaging, in that it's really a semiconductor manufacturing process that's involved in making these devices. And I'm going to quickly go through different forms of this, and many of which, if not all, enhanced also builds. There's dielectric bonding and hybrid bonding. We can build multi-layer stacks. We do oxide-oxide bonding, and as you can see my mouse hand here. We have stacked up to 20 layers of devices with DBI, and that contains 200 layers of metal. These today are obviously niche devices, but a lot of what we are seeing assembled using hybrid bonding are sensors. That probably is more than half the devices we build today, and then a lot of those are heterogeneous materials. The key aspect about hybrid bonding and DBI is that we can do very fine pitch. Here's a number of different examples. And for those of you who are not familiar with hybrid bonding, it is a covalent oxide bond, and we use either copper or nickel for the metal interconnect. The bond is accomplished at room temperature. You get a van der Waals bond, and then we come back later and we do a higher temperature anneal to drive out dangling hydrogen at the bond interface, and it promotes copper growth across the boundaries. And you end up with a structure that is as if it was sequentially manufactured. So it's virtually boundary free. And by the way, the leading edge of that technology, I go back to it, we have built things now for customers down to 0.8 micron pitch. That's below what we feel comfortable commercially producing, because our technology is really limited about plus or minus 1 micron. But as a proof of existence, the technology is certainly scalable well below 1 micron pitch. And as I briefly mentioned earlier, one of the greatest things about advanced packaging is the ability to use true heterogeneous materials. At NHanced, we have bonded together silicon CMOS circuitry with indium phosphide, gallium nitride, silicon carbide, lithium niobate, gallium and tinamide, a number of different materials. And we can do this at the very fine pitches that I've mentioned earlier. So for things like infrared sensors, we can bond gallium and tinamide to a CMOS ROIC, and often those CMOS ROICs are themselves composed of a couple layers of CMOS devices, and sometimes at different geometries. 130 nanometer analog interface for a ROIC is a nice node for a lot of technological reasons. And you can do data compression, you could do AI operations, but they often want to do that in something more like a 40 or 65 nanometer node, or even as far down, we've done some things as small as 12 nanometer FinFET technology in ROIC stacks. Another key element of advanced packaging is interposers. Certainly there are organic interposers on the market, but the vast majority of interposers still used today are silicon interposers. Silicon is still more cost effective for fine geometry than organic materials. NHanced builds a number of these devices, as do a number of much larger manufacturers around the world. An area that we're starting to do some new and interesting devices in are in glass interposers. We work with Mosaic in this area. And, you know, as a glass interposer, it has much lower capacitive coupling. It's very good for RF. And another unique aspect is that we can put waveguides into it to build photonic mixed with electrical circuitry onto a piece of glass that is perhaps 50 to 60 millimeters on the side at its maximum. If you look what's happening in the industry, there's a lot of assembly of 2.5D systems. And of course, a hot topic in the marketplace is chiplets. And the use of chiplets is just starting to appear. AMD and Intel have spoken quite a bit about what they do. Marvell in their embedded processors incorporates chiplets. And it's fair to say that the FPGAs that are built both by Intel and Xilinx, now part of AMD, are in this realm. They're fundamentally, their large devices are built of chiplets. Chiplets, in my opinion, are the future, and I'll talk some more about that. It's a fundamentally enabling technology as we move forward that allows a much faster and less expensive product creation with much lower risk. Another 3D technology that we work on, or 2.5D, is quilt packaging. This technology, and you can kind of see it here, forms almost like a zipper structure. You can see it on the side here, where pieces of silicon can be tiled together, much like a jigsaw puzzle, and solder is reflowed over those connections. This allows you to take different heterogeneous materials and tile them in a 2D fashion. The interesting thing is, because these are kind of a finger structure, you can build 3D type circuitry. This here is a mock-up. This is built by Indiana Integrated Circuits, IIC. NHanced works with them, and we actually fabricate the base structures. IIC assembles them. They are currently working on an infrared circuit that is about half the size of a golf ball, and it's built like a geodesic dome. I think the final version of it is supposed to have 96 tiles in it, or 97 tiles in it. It gives you the ability to build very unique structures that take advantage of not only 3D, but this kind of 2.5D assembly. The part that we're working on and with building this kind of cup structure actually incorporates interposers, bonding of heterogeneous 3-5 materials, as well as incorporating a 2-layer ROIC. There are 4-layer stacks that are tiled together in a geodesic dome kind of shape like this. Another promising technology is transfer printing. Transfer printing uses an elastomer to pick up dielets that can be extremely small. Small is 25 microns on the side, perhaps smaller. NHanced is currently working on a program where we're transfer printing buffers onto a passive interposer. and those buffers are on the order of about 40 microns on a side. With the elastomer, you can pick up arrays of these devices, transfer, print them from a source wafer onto a target. An area where this is being exploited is building LED displays, transferring LEDs onto a target or host wafer. It's a very promising technology. We see its application in creating active interposers basically on passive material by printing the buffers, being able to individually transfer print transistors, such as gallium nitride transistors, onto RF circuits or perhaps high performance switching power supplies. So we think this is a technology which is just starting its way to market. It's been around for a while, but I think it's just starting to get some commercial acceptance. Another interesting technology is what I'll call embedded 2.5 or 3D, really based on wafer reconstitution. Hughes Research Labs has a technology that embeds chips in a copper block that has some interesting niche applications, especially in the area of RF. As you can see here, the chips are basically placed face down on a carrier wafer. There's an interposer that's bonded to it with pre-cut holes that is filled with copper, and then you remove it off the original temporary carrier. You end up with this structure of chips of various technologies that are coplanar because they were put face down on the original wafer and then backfilled with copper. So the copper acts as a ground plane as well as a very large heat sink. There are other forms of wafer reconstitution technology around. Several of them have to do with putting die inside of silicon pockets or injection molding die that are on a temporary carrier, and you can mold around the die. ASE does this. Number of packaging, quintessential packaging companies do this type thing. This is actually something that NHanced has done. This is a DBI die to wafer assembly, and we backfill. So underneath this is an active silicon circuit. The die are then active silicon die bonded to it. The wafer is planarized and backfilled with silicon. So this is actually a completely planar wafer. This is a sonogram that was used to look at the devices after the bonding and planarization. So why is this important? Especially to compute. Let me just move this out of the way so I can see some things. Well, we're at the end of Moore's law, especially as we know it. We certainly aren't seeing the performance. If you look at the frequency, we peaked. We've been at about a 4 gigahertz maximum frequency, and it's really because we're limited by wire. The RC delay dominates these days, and there is no good mechanism to improve that. It's we're limited by physics. Another slide, and I added this in after one of the keynotes yesterday pointed it out. I find this almost staggering. I believe it was a gentleman from Intel who showed it. $500 million to do development for a 5 nanometer device. The cost is staggering. This really leads us to, if we're going to continue to do computing and evolve the technology, we have to find something that gives us more of a return on our investment, and preferably at an investment point that's 10 or 20 times lower than where the industry is headed. So as I mentioned, there's an interconnect problem. If you look at the span at 10 nanometer from an unbuffered signal, a millimeter of wire versus gate delay, there's 6 orders of magnitude performance difference. Even if you buffer it today, we're at 4 orders of magnitude. So transistors are infinitely fast. Wire is the problem. There are much better materials. You know, the Johnson figures of merit for gallium nitride and indium phosphide, gallium arsenide, using HBTs instead of, you know, FETs. There are all sorts of different alternatives and different operating points in terms of voltage and power capability that are outside those that we see in silicon. It'd be nice to be able to incorporate those. And in some cases, there's just plain a better way of doing things. There's quantum computers that are coming on the scene, and photonics of all different sorts. This is an article about light intelligence, which if you look around, I know they're in stealth mode out there, as well as a few other companies that are using this concept of being able to do vector multiply with light for artificial intelligence, and it gives you a 1,000-fold improvement. New optical switches, and this uses a unique set of materials in the article. If you went and looked at it, it's 1,000 times faster than silicon transistors. A lot of these things don't play well with standard silicon processing. Which leads us, how do we move forward? How do we incorporate all of these interesting things? And I like to think of it as we're playing with Lego blocks. How do we put these blocks together? Well, I guess we've talked about how to put them together, but what can it allow us to do? Well, first of all, photonics, it allows us to get terabits of bandwidth in less than 100 femtojoule per bit transmission. This has been demonstrated at this point by numerous companies. Tyndall has these parts that they've built and shown. Here they're actually putting them together with solder bumps, which turns out to be one of the highest power consumers in these assemblies. It is very common. Almost all the devices that we see, you have an electrical IC, which typically is done in a very deep submicron process because you have SerDes that are running at 25, 32, 56, now 112 gigabit data rates. So you have to do them in ever smaller geometries. But at the same time, silicon photonics is, they're very large structures. They're done in much simpler processes. And these are, in this case, they're solder bumped together. But if you bonded these with hybrid bonding, you can reduce the power consumption by 20 or 30% just simply by removing that interface and doing it with a hybrid interconnect. This goes from being perhaps 150 or even 200 femtofarads. This interface becomes as small as single-digit femtofarads, and in most cases, less than 20 femtofarads. This is an Intel example. Intel has been certainly busy at work looking at incorporating all of the photonic elements, primarily for communication. And there are programs all over the place in the industry that are looking at ways of doing communication and processing with photonics using multi-chip modules or 2.5D assemblies. 2.5D saves the power, reduces the footprint, gives you the advantages we really need as we move forward. Within chiplets, you know, that is again the path forward. If we look at it, Intel is building things with chiplets. The speaker earlier this evening and the Intel, not keynote, but kind of like a keynote. I can't remember what it was called, but it I believe he said this had 42 ICs on it or 47 ICs on it. It's very advanced. This is a GPU device that Intel's developed. This is a device that NVIDIA has with for artificial intelligence, AMD with their new stacked memories for the L3 cache with 96 megabytes of high performance cache and 2 terabytes of data bandwidth between the caches and their processor. And this is done with a DDI like process. It's the hybrid bonding, covalent oxide bonding. So chiplets allows us to pull all of these things together to build very unique devices. It allows us to do easy retargeting. You can change a few chips in a device such as this Intel device and change the operation. Same thing with the FPGAs from both Intel, formerly Altera, and Xilinx. It reduces the risk because you're reusing IP that you know works. And because in the best case, you can take and do everything with existing chiplets, your cost is now really an integration cost. It's the cost of developing a silicon interposer, which is ostensibly the same as building a printed circuit board. Granted, more expensive, and there is more technology to it. But at the end of the day, it is a much lower cost option than developing a 10, 7, 5, 3 nanometer chip. Another vector that we have here is really dealing with power. We can bring delivery control of the power onto the modules. Intel has done this with the Haswell and Broadwell processors in the past. M-Power is selling their technology for embedding onto silicon interposers. I know of at least one chiplet company that is developing power chiplets for integration on or into interposers. The whole concept of adding these types of devices in, hardware in the loop for power control. This happens to be an aviation device, but a number of other hardware in the loop operations are for power electronics. There's been a good example of using hardware in the loop as a way to improve the efficiency of wind farms in the United States. Another vector here is integrating capacitors. This helps reduce the IR drop and noise within devices. Integrated capacitors into silicon interposers is something that at least NHanced is currently involved in developing for customers. It also helps with a lot of the imaging devices if you can have capacitors to increase the charge accumulation that can be done with the detectors. So what's the big deal with wire? Well, wire has this problem. As we keep shrinking the technology, wire delay increases. If you think about it, when I started in this industry 35, 36 years ago, we were doing 2 microns, and wires looked like these flat planes that were separated pretty far in space. As we have shrunk geometries, our wires are really vertical structures. It's almost like we're building parallel plate capacitors with the wiring. In addition to that, the barrier layers don't scale as well. So the RC time constant of the wires continues to increase. We have more and more layers of wire. Complexity of wire is going up. And if you think of span of control, how far can I go on a chip within a clock cycle? It decreases as we go down in node size. And the thing is that, well, we are shrinking transistors at a fairly good rate. The wire interconnect is not keeping up. We saw it in the earlier presentation by Intel that they were predicting, I think it was Intel, it was an earlier presentation today in any case, that they were showing kind of at the end of CMOS, or the end of transistor shrinks at least, we're kind of stuck at about a 16 nanometer wire pitch because we have no idea how to shrink it more than that. It's hard to shrink the dielectrics and barriers more than that amount of it and still build it reliably. If we also look at wire in the context of where the power goes, a wire today can account for 95% of the power dissipation. So we have transistors that are both infinitely fast and really draw very little power. It's data movement that really is the vast majority of it. And the example I have here, it shows that perfectly. Your actual computation is, about 8% of the pie. All the rest of this energy is moving the data around. So 91% of the consumption in this case is data movement. So I think I've shown some technologies. I've made a compelling case why we would want to do these things with compute. But I want to look beyond compute. How can we use advanced packaging to move the industry forward? And I think we're at the verge of a sea change, a major change in the industry. We're busy building this bridge, but where are we building it to? We have to have a better way of moving forward with semiconductors than having is the cost of building a 1 nanometer chip to developing a new one $1 billion? If it is, there's very, very, very few applications that will ever be able to take advantage of the unique and very high performance and high compute density you could get from those kind of devices. So what I'm going to do is I'm going to talk about the current semiconductor business as being Foundry 1.0. And that business is very much focused on building better transistors. It is continuing more of Moore's law, more and more. And as we get into the twilight of Moore's law here, there is more and more real discussion about what do we get by going to the smaller transistors. We can certainly get more on a device, more transistors, no pun intended. But we're not getting really faster performance. The price is not going down. We have more and more dark silicon because we can't turn the transistors on because all at the same time because the power density is too high. So we're faced with very high development costs, extremely high capital costs, building fabs that are now approaching $20 billion. And what will the fab be when we start talking about it in discussions in the last couple of days? The 18 angstrom node. Development cycles are increasing in time. The design tools are more and more expensive, and they need to be more and more complicated because we're getting closer and closer to fundamental physics, and we have to simulate these things to make sure that we're getting the devices will work when we're done. Because if we're spending $100 million on a mask set or more, we need to make sure that we have a device which will at least come close to working on the first pass. So it's a very high risk, a very large gamble that we're making in the marketplace. As an alternative, I'm suggesting we move to Foundry 2.0. And in the previous slide, I had my steam locomotive. And I make the equivalency between Foundry 1.0 and Foundry 2.0 as the industry going from building steam locomotives to building diesel locomotives. In the era in the United States, we built more and more complicated steam engines, larger physical size, heavier, and each time they made it slightly better. It came at a much higher cost. And the industry was down to just a handful of companies that could compete with it. But then almost overnight, diesel engines came on the scene and supplanted the predecessors in the steam locomotive business. They were new companies that many of which didn't exist. And at the end of the day, none of the steam locomotive companies survived past 1969. They all were run over by the new technology. And so I don't see that Foundry 2.0 is going to run over Foundry 1.0. If anything, it may help 1.0 actually to exist and be exploited by more people. But Foundry 2.0, the premise is it's a system solution focus to get performance. It's been mentioned in some of the trade press recently. The concept of Moore's law really needs to be looked at a system level. And it's based on we're going to build with best of class components, whether they be smaller geometries or 3-5 materials or other forms of materials that get incorporated into our electronic components. It focuses on shorter wires, 2.5 and 3D integration. As I mentioned earlier, the limitation on speed is the wires. It's the RC delay. You make shorter wires. It's a square law performance improvement. So if I make the wire half the length it was before, potentially the circuit runs 4 times faster. And in reality, it perhaps runs at least 3 times faster. Most of the power goes into the wires. Wires are the limitation that we have on bandwidth, latency, power. It is the problem that Foundry 2.0 needs to focus on and resolve. So Foundry 2.0 is predicated on using advanced packaging and chiplets to solve the issues of shrinking semiconductors and getting Moore's law performance as we move forward. We can incorporate heterogeneous materials, the photonics, MEMS devices, RF devices, all of these things that I've been talking about so far in this presentation. The advantage to this approach is our tool costs are significantly smaller. Our fab costs are significantly smaller. We can reuse IP in much the same way that many of us today reuse Intel processors in the machines in front of us. It's a tool. We don't, each of us have to design our own processor. We get to leverage that past work. Chiplets allows us to leverage past work and do it for orders of magnitude less cost. It shortens development times, and it's significantly lower risk because we're dealing with components we know work. We're back to really designing circuit boards. At some level, what's new is old. It is almost like we're building 7400 series logic on printed circuit boards in the 1980s. So just like with Lego blocks, the path forward is incorporating these IP elements and really creating an IP-focused future for semiconductors. Our history is we used to build sea of gates. The problem is it was all digital. Well, we can still build we can go back actually to building sea of gates, and we use it for the digital special sauce in a Foundry 2.0 paradigm. And the reason that this is useful is because now with chiplets, we can do all of the other things that you couldn't do in a sea of gates around it, which is really what structured arrays tried to do. A structured array would incorporate memory and analog elements and logic devices, effectively gate arrays or sea of gate elements. And you did custom metallization. Well, the problem with it is it was always the wrong combination of components. You didn't have enough memory, or you didn't have enough logic, or you had the wrong kind of analog or the wrong kind of IO. It was very difficult for the industry to ever really get the target right. And so it kind of died out there. However, we're now able to really do this with chiplets. And with chiplets, you can have an infinite number of combinations. You can put down exactly the I/O or devices or analog components or amount of memory you need to make the devices work. FPGAs was kind of the next step after the structured arrays. How are we going to move forward? And FPGAs have done phenomenally in the last 2 decades. They supplanted gate arrays and structured arrays and really have been the only solution for small and medium volume customers. The problem is you have about 70 transistors for every transistor you really use in an FPGA. They're a little on the slow side. You know, you can do a gigahertz in an FPGA, which is a pretty good speed, but that's as opposed to doing 4 gigahertz logic if it was a customized scene. And they're enormously expensive because, kind of like the structured arrays, they have to put a lot of different hardware on it so that many people can use the same device. In the future, I think we're going to see FPGAs become chiplets themselves and be incorporated into this new Foundry 2.0 paradigm. So Foundry 2.0 is going to be disruptive. Today, there's no existing industry center. There's no, Silicon Valley of Foundry 2.0. We have the vertical IDMs like Intel, AMD, Xilinx, Marvell that I've already mentioned, but they're not providing services to people. They're not foundries in this area, at least. It's much lower capital cost. So there's going to be new players on the market, much like I mentioned earlier in my example between steam engines and diesel engines. There's going to be this sea change in who can be in the market. And it no longer is going to be who can come up with the $20 billion worth of capital that is going to dictate the future of semiconductors, because it is now becoming an IP-centric, knowledge-based value. It's how you can put the pieces together, how you can use advanced packaging technologies to make your new semiconductors in the market. And fundamentally, we see this as a solution for the US government, and certainly other governments in the world, to build the unique devices that they need for startups and a large swath of the commercial and industrial space. 85% of all products built are built in quantities of less than 10,000 pieces. If you're building a chip with $1 billion price tag, you've got to be building, devices that are going to run in the tens of millions per year or per iteration to make it worthwhile. This is a mechanism that allows the semiconductor industry to have a renaissance and the ability to, once again, actually have startups that are funded with, millions or small tens of millions of dollars, rather than needing to raise $250 million to do their first chip. Foundry 2.0 also allows you to do more than more. It allows you to incorporate many different technologies. And in fact, at NHanced, we've done virtually all of these different types of devices in the last 20 years, either as NHanced or as Tezeron before that. The only device that we actually haven't built is batteries in this example that comes from Georgia Tech. So over the years, we've done RF, we've done biosensors, we do microfluidics. I'll mention a little more about that in a moment. RF and antennas, photonic devices. Actually, we've incorporated solar cells into devices so that they could be light-powered IoT devices. One of the issues we're running up against, and it's been mentioned earlier today, is what do we do with all the heat as we start stacking these devices? I can tell you we have a couple of programs today whereby incorporating diamond films, we do two-phase liquid cooling. The cooling block you see in the lower right-hand corner there is roughly 1 inch on a side and is capable of doing 825 watts of cooling and maintaining the temperature of about 58 degrees C on the die dissipating that. That device can have TSVs in it, and it can be part of the 3D assembly. So there are mechanisms, and I don't want to trivialize it because this is certainly new leading edge type technologies, but there are methods at hand that will allow us to have very high density devices. And if the problem that we're trying to solve ultimately is reducing the amount of wire we have, we are on a road to higher and higher density devices. So we have to have mechanisms such as this for heat removal. Another opportunity in the more than more technologies is in the area of IoT, intelligent sensors, edge compute. These are all devices that are perhaps in hostile environments. They're certainly incorporating things like MEM devices or perhaps 3.5 materials for detectors. They have limited backhaul bandwidth. So that means you have to cook the data locally. We're facing the problem of drowning in data in things like automobiles. We can't move the terabytes of data in a car to central processing units to see where the car is going, to make these decisions. Data movement costs power, and it costs time and latency. You know, this is a problem in your car if it has to make a snap decision when somebody, you know, changes lanes in front of you. You can't take a minute to process the data. It's got to be done in microseconds and perhaps milliseconds. And all of this technology to move large amounts of data costs a lot of money. So building smart devices, building them in 3D to reduce their power, improve their performance, make them more resilient in hardened environments or extreme environments like automotive. These are requirements. And we're going to see more and more of it as the technology matures. And this really is driven by, or can be driven by Foundry 2.0. It's an ideal application of chiplets and reuse of existing technologies. So, in summary, the road ahead. The new Moore's Law is a system level Moore's Law. It'll allow us to continue to reduce the cost and increase the performance and functionality and provide the consumer with what they've come to expect over the last 40 years that has been provided by ever smaller nodes, but really is no longer available to us. Advanced packaging is a toolbox, and we have many, many tools. I've given you some examples early on. There are numerous other ones out there in the market and that are at the verge of being in the market. This is going to change the industry. The focus, whether it's exactly what I've described as Foundry 2.0 or something different, the focus is certainly going to change from only building smaller transistors to something which hopefully is more of a intellectual property, knowledge-based value to the semiconductors we all build. It'll be an incremental transformation. I've been doing advanced packaging for 22 years. And 22 years ago, if you'd asked me, I would have told you that the industry would have adopted it in 3 because it seemed so obvious to me. At this point, I do see its adoption. It is becoming pervasive, and it is yielding true value. All of our cell phones have 3D integrated circuits. Every cell phone camera is a 3D integrated circuit. All the processors that are coming out today are at least 2.5D integrated, and the newest ones are 3D integrated. AMD has no processors that they build today that are not at least 2.5D devices. Advanced packaging gives you size, weight, and power, and much more. You get cost reductions, you get risk reductions, schedule reductions. It is perhaps not the perfect solution to everything, but I think advanced packaging, it really has opened up an entirely new set of doors to semiconductors and electronics. We are going to see a renaissance of the semiconductor industry in this decade because of advanced packaging. So last punchline here, advanced packaging is driving an industrial revolution in semiconductors. And my belief is it's enabling Foundry 2.0. Thank you very much for your time. And I will take questions as I have time here.
Okay, thank you. Thank you very much. Good talk. So we have time for a couple of questions. So if you have any question, please use chat window or please raise your hand. Okay. Okay, so I have a question. Okay.
Yes.
Okay, so Bob, so you talk about the Foundry 1.2 and Foundry 2.0, okay? So,
yes.
You know, everyone know the IDM scheme finished, okay? And then now we have Foundry and the design house, right? Foundry
Yes.
are completely separated, okay? And this scheme will continue in Foundry 2.0? What do you think?
I think it'll be very similar. I think Foundry 2.0 may be the foundry that designers interface with. I think you're going to have two different sets of designers. You're going to have designers who design chiplets, and they're going to primarily interact with Foundry 1.0 as their vendor, and Foundry 2.0 as their customer. And the people today that I used to know as customers. When I started in this industry in '85, I had a design house here in the Midwest of the United States. And we had dozens of customers who developed their own chips. But they have gone away because they are not in a position to spend the millions or tens of millions of dollars. I think that they will be the customers of Foundry 2.0, because Foundry 2.0, it's in this strange space between what today's foundries are and what today's OSATs are. And they will do a function that looks kind of like an OSAT, kind of like a contract manufacturer in some ways.
Okay. So we have one question from the Dr. Gabara. So what percentages of the products being sold today are Foundry 1.0 versus Foundry 2.0?
Well, I would say virtually all of them today are Foundry 1.0. Now, I would caveat that or point out that in reality, Xilinx, Altera, Intel, AMD, and at least some of the products at Marvell and even some of the products at Broadcom and Qualcomm really are in the Foundry 2.0 model. They are chiplet based. Marvell has probably done some of the most interesting things conceptually with Foundry 2.0 in that they have a family of chiplets that by mixing and matching them, they can target different market segments that otherwise they wouldn't be able to do with their embedded processors. AMD in that same vein has been able to address different performance points with customers by having more or fewer processors, bigger memories or less memory. So it is using the idealism, certainly of Foundry 2.0. But today there is no Foundry 2.0 entity, but I believe that we're going to see some soon.
Okay, thank you very much. So it's time to finish. Let's thank the Bob. Thank you again.
Thank you very much.
Okay.